I'm Janice. Don't know if we're recording right now.
We are recording.
Okay, great. So I can run you through this Tellurium, Antimony, and Live Roadrunner introduction. This notebook was written by Veronica, but I will present it today. So here is the notebook, and you can download this notebook in our shared drive. It's called the Tellurium Introduction Notebook, and here are the table of contents. And here are the links to the relevant resources. So we have the Tellurium installation instructions. I believe this is for if you're working on your desktop. There's going to be documentation for each of the tools. But for right now, since we're working in the notebook, we'll just go through it. So Tellurium, Antimony, and Live Roadrunner support rapid simulation and analysis of kinetic models. We have here, this is the Tellurium package. So if you download the Tellurium, then you get standard support, which include all these standards. You also get modeling support, which includes Antimony that we're going to talk about, and Live Roadrunner. And Live Roadrunner is the modeling engine. It has all these modeling features, and it comes also with utilities for visualization, parameter scanning, and file utilities. And Tellurium is a Python package. So if you are modeling, then you might want to also use NumPy, SciPy, other things for visualization like matplotlib, and so on. So what is biochemical network modeling? It's basically chemical kinetic studies. Chemical kinetics studies the factors that influence the rate of chemical reactions. So it's kind of like how concentration, temperature, light, that affects the rate. And we can build chemical reaction networks. We can build dynamical models of chemical reaction networks. So those can be things like genetic circuits, cell signaling pathways, and metabolic networks. There are different types of biochemical networks like agent-based, algebraic, and Boolean networks, just to name a few. But all of these networks can be represented using the Tellurium package. So the reason that we perform network modeling is to understand subcellular processes, drive experimentation, and one important thing is make predictions about a system behavior. So that can be used for say designing drugs or novel disease treatments, and providing a basis for larger multicellular models. So later on, you might learn that when we build large models, we start small and we kind of build it in chunks. So yeah, there are different types of network models, and these network types span different time scales, as you can see in this picture. So for example, there's gene regulatory networks, protein signaling networks, and metabolic networks. This is one example of a metabolic network. Here you can see it's a glycolysis pathway of Lactococcus lactis, and it's complicated, I suppose. If this is the cell boundary or the cell wall here, there's a lot of metabolites that are going through in these different reactions that I believe are numbered. This is a protein signaling network. So yeah, there's proteins that are going into formation, phosphorylation, dephosphorylation, degradation. So this is just another example. And here's a gene regulatory network. So as just P1 going to P2 and degrading into whatever. This is another example. So here's a repressolator model by Elowitz and Liebler. It's a repressolator circuit, and in case you don't know what a repressolator is, it's basically a loop with at least 3 genes that express the next gene in the loop. And so here, these blocks are the promoters, and the TET-R promoter promotes making this TET-R protein, but that protein will block the transcription of, it will repress the transcription of the CI protein, and so on, and it goes in this loop. So Elowitz and Liebler were able to run simulations, and you can see how like the protein levels, they rise and fall in these oscillating manners. So the yellow, the red, and the blue kind of correspond to these colors. And what they did was they simulated their model first, and then they built up their model using actual gene circuits in vitro, and they were able to observe what they simulated in actual, I believe this is E. coli. So you can see how like it's dark here, but the E. coli start, this particular cell that this arrow is pointing at starts flashing, or I guess expressing fluorescence in a oscillating manner. So it's glowing here, not glowing here, and then glowing here again. And this is the fluorescence that it shows. So you can see the oscillation. So that's just to show that simulating these networks can be used to, what's it called, model real world things and help predict what would happen. Here's another example of respiratory or oscillating network. This is the Jana-Wolf network, and you're going to see this later on in the week. You'll probably use it to help as a test case for other tools that you might learn about. And this is just negative feedback and ultra-sensitivity network here. So we're going to jump into coding right now. Right here, we're going to first install the package. Oh, before I start, does anyone have any questions? Okay, so first, to start off, we're going to pip install our Tellurium. If you're following along in the notebook, we have to make sure that there is a exclamation point when you install this package within the notebook. So I'm going to run this. After I install it, I'm going to import the Tellurium as TE. And this might take a little while, but it shouldn't take too long. All right, anyway, while that's loading, we're gonna first start by writing a mass action rate law. So here we see that there's a species S1 and it goes to S2 at a rate of K1. So that mass action rate law would be K1 times S1. So like the concentration of this times the rate of this rate. The way to do that would be to write an antimony string. So what we would do is we start off with these 3 quote, this is a 3 quote block and you have to end it with a 3 quote block. Sometimes you can specify the species. We'll see later when we have to, when it's absolutely mandatory that you specify the species, but not in this case. So this is the reaction name, J1, and then when you put the colon, it kind of signifies that that's the reaction name. You can name it whatever you want, but customarily it's called J1 or 2 or whatever number. Here's your first species, and we're gonna say that S1 goes to S2. So this is the actual reaction that we write. To denote the end of the reaction, we put a semicolon, and then we write in the reaction rate law, which we determined was K1 times S1. Okay, then we have to assign the species initial conditions. There is, I believe, a default number to it, but so right now in this model, I'm going to say that S1 we start at 10 and S2 starts at 0. And we're going to assign a constant value to the global parameter. So I'm going to say that K1 is equal to 1. So once you write that all down, then you can run it and save it into this variable called ant string. And then once you write this, you can actually now start simulating. So here's the actual command to load the antimony model into Tellurium. So it's te.load a, and you put in your antimony string. You can put in this actual, like you can copy and paste this into these brackets, or you can save it as a variable and put it in. And then you can save that as a variable. So that becomes like your Roadrunner object. And with the Roadrunner object that you have specified all your conditions and your reactions with, you can simulate that. So here we have a Roadrunner object. We're going to simulate it. And the simulate method takes in a few arguments. You need to start with the start time, the end time, and then the number of points in between. And that will give us the result. So here we can, I will show you exactly what the result looks like. Oops, sorry. All right, so this result, after you simulate, you get a named array. And basically that means like the first, I guess each column is defined. So the first column will tell you the time. And as we specified, it goes from 0. And if I scroll all the way down, you'll see that it goes to 10. And there's 250 steps in between. The second column is the concentration of S1. And there will be the concentration of S2. So the concentration of S1, we said that it starts at 10 at time 0, and then as time goes on, it'll change. And we started S2 at 0 right here at time 0, and then it will also change. So these are the raw values, which can be useful if you're, I don't know, doing like data entry, or sorry, not data entry, data analysis, but you can also visualize this with plots. So to plot the simulation, you can put in your Roadrunner object and write plot. It takes in a couple keyword arguments, but these are all optional. So here, let me show you what that looks like. This is a plot of the simulation. So without a simulation, I don't believe it will plot. All right, so does anyone have any questions so far? Okay, all right, so now we're gonna set and get values with Tellurium. Right here we're going to go back to our ant string, the one that we wrote earlier, and we're gonna load it once more. And you could say if you wanted to change the parameter value. So say we wanted to change it to 5, we could actually scroll back up and change K1 to 5. Then we can reload the string and simulate it. Or if you want, you can just load the string and then change it, like change the parameter value inline. So that involves taking the Roadrunner object and then whatever the name of the parameter value is. So it's r.k1, and then we're going to change to 5, and then we can resimulate it and plot it. So here you can see that the rate is much faster initially before it hits steady state with when k1 is equal to 5. You can also do the same for species. So here we're going to change the species S2 concentration to 10. If you recall, it was originally 0. So we're going to do the same thing here. And you can see that it changes. And this is the plot for that. You can also check current values of parameters in species. And that just involves here printing it out like in a nice way. So I can just show you that. We're going to get the value of species S2, that's r.s2 or r.k1. Generally, I just, if I'm working on my code, I just type in like r.k1 and it'll just print that out for me. So yeah. Right. Now we're going to move on to resetting your model with Tellurium. So I just want to emphasize that this is very, very important. Resets are very important because they allow you to run multiple simulations without reloading your model each time. And that can be important, especially if you have a large model. So our antimony string right now, I believe it had 2 species and 1 parameter value, K1. But if you have a model that has like thousands of species and thousands of reactions, then that might take like time on your computer and computing power to reload that every single time. So what you would do instead is you would just reset it. Okay, so we have an antimony string, we simulate and we plot. This is what it originally looks like. When we can change the value of K1 and rerun our simulation. So I'll run it and I'll show you exactly what happens. Nothing happens. And the reason that happens is because when you simulate the first, okay, so we loaded the antimony string, we simulated it, and then it reached steady state. And the Roadrunner object kind of holds on to that, like holds on to where that, I guess, model is or how much it was simulated. So once you change the parameter value when it's at steady state, there's actually like nothing for it to do because it just retains where it was. So if you want to start again from the beginning with this new parameter value, then you would have to hit r.reset, then change the parameter value again, and then simulate your results and plot. So now we get what we saw earlier when we reloaded the antimony string model, but now we don't have to reload it, we can just reset it. If you want to reset the parameter value, so say we don't want K1 to equal 5 anymore, then you would have to hit reset all. And reset all changes the parameter and species values back to the antimony string that you loaded. So here I'll demonstrate this. All right, so we get back our original plot for our simulation. Okay, does anyone have questions about resetting? All right, okay, so now we're gonna go over adding events to an antimony string. Here's our antimony string. This is a little different. So like I said before, we can add species at the top. That's not always necessary, especially if they're in the rate law. So here we had S1 and S2. So we don't have to write species S1, S2. However, if the S20 does not appear in these rate laws, then you have to write in species S20. Okay, so we have the same rate law, reaction and rate law, and we assign the values. And here, if we want to assign S20, let's say that we want S20 to be a function of time, the cosine of time. So we would write S20 and then colon equals and then cosine of time. That's just one example. We'll have another example next, but we'll have K1 equals 1, and then say we want to add an event. So say we're modeling a drug and we want to say that at time 5, we added more drug. So you'll get a spike. So at time greater than 5, S1 will go back to 10. You write the string, you can just load it, simulate, and plot it. So that looks like this. And you can see here we have S20, it's having that nice cosine wave. And at time is greater than 5, we get back this sharp point where S1 goes back to 10, and then it starts doing its own thing. Right here, I want to say that when you're simulating, when you're simulating and plotting, the numbers work out even though it might not look like the plot like reaches all the way to 10. This is because like if you plot it at a coarse grain, it might not look like it goes to 10. So if you plot it at a finer grain, then it does start to like match up visually. Okay, so here's another example. Let's say we have species S30 and we want species S30. This is how we would write a piecewise. So piecewise, you would write piecewise 0. This means that it's 0 at time less than 5. It's 5 at time less than 10, and then it's 10 everywhere else. So remember that this requires a colon equal sign. And if we were to add an event, say we wanted to have a spike in S1 whenever S1 fell below 0.005, then you would just write it like this, where it's a colon at S1 is less than 0.005, another colon, and then it's S equals 10 or whatever value you want. So we would do load it, simulate it, and plot it. All right, so there's our piecewise. And then there is our spike that keeps happening whenever our S1 dips very low. And then S2 is doing its own thing. Okay, so now we're gonna move on to actually modeling, I guess, more complicated systems. This is
Candace,
the
you had a
yes.
question just to recap the piecewise equation.
Oh,
It's a
okay.
little slightly confusing.
Okay, so sorry, what? Okay, I guess I can go over it and then
Yeah, just in a little bit more detail, I think is fine.
okay, so yeah, if you want to write a piecewise equation, you would put in your I guess species, then you do in the colon equals, and then you write in piecewise. So you have these brackets and you put in whatever you want in the brackets. So I guess I can also like format it this way so it's easier to see. But you would just define what that value is here, and then the condition, and then you kind of just list it with the comma. So it's the value, the condition, and then just keep going on with the value conditions, and then the default value after all the conditions are met or passed or whatever. Does that answer your question or?
Show the graph at the same time.
Oh, of course, yeah, sorry. So yeah, there's 0 right there before time 5. And then it'll just shoot up to 5 at time is less than 10. So after you what's it called? Meet this condition, right? And then when time is less than 10, then it'll go jump to 5. And then when time is not less than 10, it just becomes 10.
It might, so both things are true at the beginning. If time is less than 5, then time is less than 5, and it's also less than 10. So it goes through an order. So it first checks the very first condition, and if the first condition is false, only then does it fall down to the second condition.
You can have as many piecewises as you like, can you? As many pairs as you like?
Yeah, as many pairs as you like, and it'll just go through them in order and it'll return the first time it finds something that's true.
Yeah.
You don't technically have to have the last one if you've covered all your conditions in the first few.
Yeah, right.
But usually you need something to fall through to.
Yeah.
Sort of the final otherwise.
Oh, and somebody asked what's the difference between equals and colon equals?
The colon equals means always equals, like throughout the whole simulation, and an equals is just equals at the beginning of initially equal to.
So the colon equals is basically part of the model itself during the run,
right? So
it's always executed continuously.
So normally reactions control the levels of species and stuff. So you start off at 10, S1 starts off at 10, and then it's controlled by reactions. But if you have a value that's not controlled by reactions, you can say this is just the formula that it's equal to. And then it's always, whenever you want to know the value, you just plug in the current time and the current model state, whatever that is, and calculate the value of it.
So this is like these are the fixed species, right? Like this would always be a fixed species.
Someone wants to know, write a piecewise so it does the same thing repeatedly for however long the duration is. You would just have to write your conditions cleverly. You don't have to put time in the conditions. You could have like S1 in your conditions or something.
And the numbers can be other variables, right?
Yeah, and the numbers can be other variables. You could say that when time is less than S1, or I mean, that's kind of a silly example, but if S1 is less than you could have something that is 0 if S1 is less than S2, and 1 if S1 is greater than S2, or something like that. And then if S1 and S2 kept switching, then your value would also keep switching.
I mean, you can do a lot of magic with piecewise. as you can imagine.
Worked for spiking. Yes, I mean, so the spiking was done by the event. That's probably the better way to do an event, because if something is being controlled by a reaction, you don't want it also, you can't have it also being controlled by a piecewise equation. You have to have a separate thing controlled by a piecewise equation.
Yeah, species is a concentration, and a species is any molecule in your model.
Yeah. It can mean amount instead of concentration, but it's a slightly advanced thing.
Oh, that's illegal syntax.
Yeah, that doesn't work.
So the A equals 1 you have there, that has to be an expression like you know, K times A or something. There can't be an equals in it. It's got to be something that computes to the value of the rate.
Yeah, if that was a new line, then A would start at 1, and if the dollar sign means it doesn't change, it is not changed by reactions, so it just wouldn't stay at 1, I guess. But
that sounds complicated.
yeah, I don't know. Anyway,
it depends what you're trying to do there, right? What your objective is. So you want A to be constant, and then you want to set A up to some initial value. Is that it? So Javid?
I think that's what the question was. If you make A a boundary species and then you set an initial condition, or you set it to 1, so it's a constant value at 1, is that the same as using the...
Oh, I see what you're saying. I guess so. Yeah, I wouldn't do it
effectively
that way,
it is.
Yeah.
If you put a colon equals 1, then there you are asking the computer to do more calculations. It will always check. It will be continually assigning 1 to the value of A, as opposed to just not leaving it alone. And
I wouldn't do it that way. It might work.
It probably would.
It probably would work, yeah. But I would do just what you had before: $A reaction, and then then set the rate to then set A to 1.
Someone also asks if you can set a constant derivative, and you can. Basically, again, if you want it to not be controlled by reactions, you can say something like A prime equals 4, like that. And then that's the rate of change of A is 4. And again, you could put K prime equals K1, something like that. And then that's the same as having a single reaction that creates A at a rate of K1 times A. But again, in that case, you can't put A in any other equation. You can't put A in any other reaction. You can't have it changed by any other reaction.
But you can put it in other derivative equations.
Right.
Yeah. Lots of good questions.
Okay. Keep asking questions, but I think I'm going to move on right now.
Yep.
Okay, so we're going to write an Antimony model with interactions, and this is the repressolator that I showed you earlier. So it's actually written out here. This is the repressolator antimony string, and we have species M1, M2, M3, and P1, P2, P3. They're supposed to stand for these, what's it called? Proteins here, LAC-I, TETR, and CI. And all of these reactions are basically like the production of mRNA. I try to put this in line. The production of mRNA, you can see the degradation of mRNA, the production of proteins, and like the degradation of proteins. And that's just for one protein and mRNA 1, 2, and 3. This is the rate law. So this just goes, this is just like how the mRNA is being produced, the rate at which it is, and there's going to be like a basal leak. So even if repression is like at 100%, like there's going to be a basal rate that the mRNA is produced. So that's why that's there. Here are the species initializations, and they're just very long decimal numbers because we optimize them to generate oscillatory dynamics, and the same applies for the parameter value initializations.
One thing, Janice, can you comment on the, I noticed that line 8, the reactant is missing.
Oh,
You know, yeah, you're allowed to omit reactants or products if you don't care about them. You see that? It's got the line arrow with no name in front of it. Line 8.
Sorry, there's
Where
no.
where the cursor is.
Yeah,
Oh,
what
yeah.
you highlighted. That's it. That's
You
it.
highlighted it,
You
yeah.
Okay.
highlighted it.
I
There's
highlighted
nothing
it.
there.
Okay, yeah, so there's nothing there, and this also goes to nothing.
You're allowed to do that, yeah.
Mhm. Oh, and then something I forgot to mention up there is that if you have, I think all of the reactions that I use just go from like one species to another species, but you can always put in like if you're gonna make 4 of them at a time, you just put in 4
Oh, yeah.
or 6. It's like very, I guess that's how it works.
Yeah.
Okay, so all right, so I am going to run this to save this repressolator string. And then we're gonna load the repressolator model, and we can save the repressolator model in SBML format. So SBML format is it's basically a standardized format, and it's useful for exchanging models like across different software or across different platforms. And it's basically another description, model description format, just the way that antimony is a description. So SBML is a different one. The way we do that is we call in Tellurium to save to file, then we put in the file name, and we're gonna ask the repressolator object to get current SBML. And then I'll also simulate and plot it to show you what that looks like. So this is our simulated repressolator model. And I guess we saved the file to the SBML format. All right, so we can reset the repressolator. And there are some really handy methods with Tellurium. So this repressolator, we were given this repressolator model. This is not a model that we created. So if I wanted to see like what are the variable species in the model, or what are the parameters or the current values of the parameters, then I could run the respective methods. So here we have get floating species IDs, get global parameter IDs, and get global parameter values. And that will just kind of print out all the species IDs, parameter IDs, and the global parameter values. And I believe that these parameter values, they match up with the global parameter ID. So the first one would be AM1, and then the second value would be KRP3, and so forth. Okay, so here we have, wait, I think there's a question. Oh, okay. Anyway, so, okay, so here we have SBML description format versus human readable antimony string. So we're gonna talk more about standards in system biology later, but I kind of want to show you the difference between SBML and antimony. So SBML is a standardized format, but it's really hard to write in SBML, which is why antimony was created. So when we're going to reset the repressolator model, and then I'm going to show you exactly what the SBML format looks like by printing it out. So this is the SBML of the repressolator model that we just ran, that we simulated. You can see it looks, I believe it's like XML based. So it's just really hard to read. You can see that there's values here, but writing this would, I believe, be really hard. So this is in contrast to the antimony. So again, we have the repressolator. If we say get current antimony and we print it, then this is the antimony form that I was showing you earlier that we wrote in. And one thing that I want to kind of distinguish is that get current antimony gives you the antimony format of the model that you have. So if you change the parameter value, then this would also reflect that. Whereas get antimony, it would just give you the antimony that you loaded in initially. Okay. So now we have exercises. Are we gonna go through this like all together, or should we put them in breakout rooms? I don't remember.
We've done breakout rooms before.
Yeah, we have done them.
Try that?
We could try that.
Okay. Back now. Does anyone have any questions that they had in their breakout room that you want us to address as a group?
I can mention some questions that were asked in our group. One was, do you have to declare the species at the beginning? And the answer I gave was, no, you don't, unless you're using compartments. Then you have to specify what the species are and which compartments they live in. Otherwise, you don't have to, have the line species S1, S2, S3, etc. Because the compiler will figure out what the species are and parameters are from the model.
The other reason to declare species is if a species doesn't appear in any reactions, but is a species anyway, then you have to declare it as a species.
Oh, yeah, that's right. Yeah.
So if you were just setting the rate law directly with S1 prime equals K1 times something, then you would want it. You would want to say it's a species. That's
true. Another question was, what solver do we use? We use CVODE, which is a stiff solver. There are two other solvers. They are RK45 and Euler, but those are only needed for we never use them actually.
They're still available in
they're available, yeah. There was a special use case for Euler, believe it or not, which is the simplest integrator possible. There was a very special use case, which is why that went in. And the RK45, I think that was just there to check something, but the CVOD is a very, very robust solver. The other question was, if you only ask for 10 points, does that mean it's going to jump and not give you very accurate results? No, that's not the case. What happens is it'll integrate whatever steps it needs to maintain accuracy and just give you the points you asked for then from that run. So you're okay. You can ask for as few points as you want, and it'll still be accurate. But any other questions from other groups?
No. Go ahead, Lucian.
I was going to say, yeah, someone was wondering, like, is it possible to get SPML models? How would you get an SPML model from JWS Online or somewhere else into Roadrunner? And you can download it, and if you download the file, you can load it with load S instead of load A for loads SPML. And you can also you can load S with a URL of the link directly of the SPML model, like from biomodels or something. There's also more questions in the chat. Let's see here.
Kyle asked why we don't need the keyword end at the bottom of the antimony string, and I don't know why, but yeah.
So that is, if you define a model, if you give the model a name, you say model 1 colon whatever, and then you have the model, and then at the end you say end. But if you never give it a name, then it gives it a default underscore model name or something internally. And then you just, so either you have the model, the word model and your name, the model, and then end, or you just have your model. Both will work just fine. The reason to name your models is if you're going to be building models up, or if you just want to be fancy.
Any other questions from other groups? No? Okay, do you want to go over the exercises then, I guess?
Oh yeah, we can do that. So I'm going to try to share my screen. Okay, so believe I'm sharing my screen.
Yep.
This is exercise 1. I can go over, I don't think we need to go over this one because it's just like looking at things. Okay, so but the exercise 2. So this is the exercise 2 solution. We have our 3 quotes. Oh, I just realized that this is like single quotes. But yeah, anyway, we need our 3 quotes.
Either one works, yeah.
And then we would define our reactions J1. And that we put in that S1 goes to S2, S2 goes to S3, and it has the rate V1, which is equal to K1 times S1. So that's right here. And then K1 times S2. These comments are not necessary, but they're there just in case you wanted them. And then we have K1, we have to define all the parameter values and the species values. So we were given the parameter values and the species values here. So they're just right there. You can write them like with each line and forget the semicolon, or you can put them all on one line and have the semicolon there as well. Okay, we have the exercise 3 solution. So to load the antimony string, it's just, we call on Tellurium, load A, and then the ant string. I noticed that someone asked like how to load what's called SBML file. So that would just be Tellurium and then load S, and then whatever your SBML file name is, or the actual string if you have that. And then
Or
we
the
can
URL.
yeah, the URL. And then we can also like simulate it by running R. So we call on the object r.simulate, and then we ask you to do it from time 0 to 20 with 50 data points. So it's just 0, 20, 50, and that's what you should get. Okay, so it says plot the simulation. So we run R plot, and then if you want a title with the axis labels, then that's what you would do. So this is a plot that you should get. And if you reset your model and plot only the time of the species S2 time course. Okay, so this is what this looks like. You would run r.reset, and then you would run simulate 0, 20, 50, and then there are other arguments. So you would add in the second argument. This is, I believe this is like is it called a tuple or tuple?
Oh, list.
A list, sorry, thank you. A list. Okay, so you would write in your list of what exactly you wanted to plot. So here we want to plot time and S2 because we were asked to for the S2 concentration. So then you would plot that, and that's what you would get. So those are all of our exercises. Here's our acknowledgements. These are the developers behind Tellurium, LibRoadrunner, and Antimony, and our funding sources. And this is our bibliography.
Okay. So are there any specific questions or topics? We've got technically half an hour to go. So are there any specific things you want to go over again from this morning?
That's a question to everyone, not me, right? Like,
Anybody? That's it. Is it, Janice? You've done that's your bit, right?
okay.
I think, yeah. You haven't got anything else, right?
No, I don't.
No. Okay. So, if there's any questions or stuff you want to go over again, now's your chance. I mean, we'll be running a lot more Tellurium stuff tomorrow. I usually give an impromptu session as well. We would just try all sorts of different things.
I have one question.
Yeah.
Each run of Tellurium, if we specify the same starting condition, will yield the same result.
Yeah, in theory.
I'm just asking if there is like some randomness introduced by the model itself. Or...
Okay, so normally when you run them again, the same initial conditions, you'll get exactly the same numbers, right? It's exactly the same trajectories. Now, Now you can try to run, you can run a stochastic simulation, when of course then you'll get a different run each time. You can randomize the initial parameters each time to get a different run, but normally if you run a model without any changes, each time you run it, you get the same answer.
Okay, thank you very much.
Okay. I mean, sometimes, I might randomize the initial conditions and I'll just run, maybe 100 simulations just to see the effect of how sensitive the model is, perhaps to, changes in a certain parameter. That can be quite useful to do.
Yes, but that was exactly what I was asking, like if the simulation given the same starting condition will yield the same result.
It'll give you
For
exactly the same
stochastic
results.
Simulations or other use cases, exactly as you are mentioning.
Yeah, but if it's a stochastic
understand.
simulation, then yeah, you'll get a different answer every time. But let's say you
Yeah.
wanted a quick way to know, how sensitive is the model to a certain parameter, and you didn't want to do a sensitivity analysis. You could randomly set that parameter to different values, perhaps using a normal distribution, and then run each simulation then, and you'll
Can
get
this be
100.
specified in the antimony string, or should it be specified?
No,
You
it would be
can-
specified in the script probably.
I mean, you can do
actually-
it. You can do it in Antimony also. That's
Ah.
a thing that was relatively recently used. But you can say S1 equals normal parentheses, and then you give it the mean and the
Oh, maybe we could demo that.
yeah.
That's super useful.
Yeah, when can you
Yeah.
demo that then, Lucian? Because we got
Let
half an
me
hour.
see if I
so-
can.
Yeah. Janice, do you want to unshare?
Oh, I might be able to. Yeah.
Let's try this crazy idea.
So crazy. Let's see.
I've never done this myself directly in Antimony, so.
Oh, really? Oh, it is not the right one. Here. Share my other screen. That actually has. There it is. All right. So let's see here. Okay, yeah. So if I want S1 to not be equal to 1, I could actually say normal, and then I would say center it 3 with 0.5 or something. And we'll try that.
The colors
And
on
now
the screen
S1
are
started
weird.
at 2.5, right? Or if I run it again, oops. If I run it again, now it started at a little over 3. Run it again, starts at, again, a little over 3 or something. So, and we could make it more dramatic by giving it a bigger, whatever that is, that parameter, right? That wasn't more dramatic
But
at all.
I tell you what, do it.
Yeah, there we go.
Set it to one of the parameters. It said K1 or K2.
Sure.
Then it'll maintain the same axis. Then, if you set then S1 to 3.
1, and say 0.01 or something.
Yeah. And then set the S1 to 3. So that means the y-axis won't change every time.
Sure. Yeah, so there's 1. Click back here and run again. Or here, what we can do is we could actually just put this in a loop.
Oh yeah. Yeah, the only thing is you have to tell plot to hold.
5.
Or you
And
can-
then do that. There. That wasn't very exciting because I put it to. So we'll have
you
it-
can see some differences.
that's right. Here, we'll make it more dramatic. There we go.
Yeah.
So there's our 5 different things with 5 different values of
Yeah.
K1. So that was yeah, a K1 with a value of 0.1, varying around about 0.1 with the same deviation there. So yeah, you can put it directly in the model. Obviously, the other thing you could do is if you just had this be 0.1, is you can say r dot K1 equals what, math dot normal or something. Then I have to like import math somewhere. I don't remember if that's going to work. No, I don't know where I can get normal from. Do you know where I can get a normal distribution from Python? Anyone?
Random. You have to import random.
Import rand or something.
Yeah.
So I say like random, like, will that work?
I'll just have a look. Let me see.
Yeah.
You should be able to get.
Random.random.
Yeah,
NumPy.random.
NumPy has a random, module.
So here, can I do that?
Yep, that should work.
Ooh, there we go. Look at that. Nice.
Your color scheme is really weird.
So just the default, whatever it is.
It's really light for some reason. Because the big question is, let's say you wanted to plot one of the curves, all on top of each other.
Oh, then you'd have to like save them all, right?
But you can do it with our plot, but I can never remember. It's easier to do it with matplotlib.
So
I think if you turn off the show function for plotting, then you can just wait until the end and then do.
Yeah, something like that.
Right, but
What's
r.plot
that
is like our version of hooking into matplotlib. So
But I think it has a show thing in it though. It has an argument, but I've never used it much.
From matplotlib dot, what is it? Plot something? PL plot. Oh no, that's it. Here. Import that as
Yeah, but you'll have to
plot bracket 0. And in fact, here we could whatever.
oh, I see. Then you go results.I, is it?
Like 1 colon or something. Is that going to work?
You don't have to add it. I don't think you have to add the result onto the result though.
Okay. Do I?
Because it'll overwrite it each time, so you're fine.
Well, oh, I should. So I could just plot it and then yeah.
You don't need the result equals result plus result. Yeah.
Right.
That's it.
Didn't like index list out of range. Didn't quite like that version.
It should be results.
Results.
It should be :1, I think, shouldn't it? Oh, it's result.
All right, it's a result, not results. It's the other way
I
around.
think it's
colon.
I think it's :0.
Good Lord, what happened?
You hit the keystroke that brings up the
I'm like
thing.
tabbing into random things. Here, I'll just reload. Okay.
So I think it's :0 and :1.
Yeah, that would make sense. Colon, comma, 0, and
I don't think it's a comma.
is it just a space?
No, nothing. It's just :1.
I think it
Yeah,
should
that's
be 0, comma, colon, and then like.
There.
No, you want
column
all rows. So it has to start with a colon.
Yeah.
And then you specify the column.
Comma 0. Yeah. That should be right.
So it's
I don't think you need the
comma
comma.
0 is
I don't think you need the
colon comma 0 is the first, is just time. Colon comma 1 colon is everything. So
I don't know if you need the other. Anyway, the other thing you can do
This
now is
works,
just select one of the species, like S2 is the most interesting one. So go comma time and S2. Right, so that'll give you just 1, and then you got a -1. That's because your normal distribution
yeah,
is
normally
dropping below,
yeah.
and then you can do it, 100 times.
There we go.
Yeah, you know, you want to reduce the standard deviation just to
Probably.
try to limit the negative. No, make it smaller.
Oh, the 0.05, right?
Point, yeah, or 0.01 or something.
There
There you go. That's a bit better.
Nice.
No, that's okay. So that's one way you can do it, by directly adding the thing to. Oh no, you did it there, didn't you?
So in this one, I put it here.
Oh yeah.
But I could also just say
You could have put it in there as well.
I could have put it
yeah.
in the model itself. Yeah.
Yeah.
Normal 5.
Oh yeah. Okay.
And I can take out this line and do the same thing. Yeah.
Oh, there you go. Nice.
Lucian, can you copy and paste this into our Slack channel?
Yes, I can.
Please?
Sure.
So I'll probably doing a bunch of this kind of ad hoc stuff tomorrow morning.
Yeah.
Okay, good.
Right, there it's in the Slack.
Great. Yeah, it actually works. One thing that has puzzled me is how you can get a distribution that doesn't go below 0.
Oh, you can set borders. And I think with a normal distribution, with if you want a truncated distribution.
Yeah.
Here, I'll share my screen again. I think it's just the next 2 arguments.
Oh, I see.
So just like with this, we were getting some things.
So you notice those of you here, some of the trajectories went negative. That's because it's giving a negative K1. Oh, I see. 0. Oh, is that all you do? Okay.
That's all you have to do. You have to set the lower bound as the first argument, and the upper bound as the second argument. And inf counts as infinity. So if you want no bound, then you do that.
Right.
So we could go back up to like a 0.5.
Oh yeah, right, yeah.
And then we should get, it still never goes 0, but we get to more extreme values up, up above.
Yeah, I see. That's good. And you got other distributions other than normal, I assume.
Yeah, normal and uniform are the standard 2. You can get a Poisson distribution. You can have exponential. And there's I think there's like around 10 or something. And these are all in Antimony that copies exactly what is able to store in the SBML. So the SBML defined like this set of particular distributions in one of the extensions to SBML.
Right.
That's the only thing you might have to worry about if you make this. Oh, in fact, here, let's do this. Get current SBML. So there's the thing, and then here's all your here's the model itself in SBML, and you'll notice that up here there's this distrib namespace for a particular extension to SBML, and it says here that that namespace is required, which means you have to have it in order for your model to work the way it was designed.
Oh, I see.
And then it's actually just used in the MathML as a C symbol. This is getting a little bit technical, but here's your normal. So that's where it's actually used. So the only issue with doing these distributions in Antimony and then in SBML is that there are some interpreters of SBML that won't understand distributions, and it should hopefully it would complain at you productively and say like, I don't understand distributions, but but Roadrunner understands distributions, so you're good on as far as that goes.
Yeah, okay. I wonder if there are any other questions.
One person asked, is there a way, good examples of building models graphically, tools that you can use for that? We have some older ones ourselves.
We're actually developing a completely new one at the moment, using Qt. It'll be cross-platform. It'll be a library as well. So if you're a developer, you can host it in your own application. But that won't be ready for another year or so.
So is SBW still a thing, or?
Yeah, SPW is still a thing. Yeah.
Can you build something like that in Copasi?
Well, yeah, no, Copasi won't let you. Copasi will only let you view networks. Won't let you build them graphically.
Okay.
But we have an experimental Python thing called Coyote, which lets you draw networks and export them to SPML. There's Pathway Designer, but that's Windows only. But the new one should be very fancy when it comes out. So yeah, watch this space. Will we talk about
agent-based models?
Nope.
Yeah.
That's for next week and the week after. I think there's two more. These courses are done. We organize them together, and agent-based will be a focus of next week and the week after.
But that's a different thing you have to sign up for separately, right?
Yes. Yeah,
Okay.
we don't do that. We work with the guys though, but we
Is that the Glacier Lab?
Yeah, and the Macklin Lab. Yeah.
Okay.
Yeah. Where can you sign up?
Yeah.
Good question. Let me see. Let's see. Let's see. Front page. Yeah, if you go to this, if you go to this page. Yeah, that's right. Yeah, there you go. Connor has it as well. So in fact, we're working with this group as well to build a completely new agent-based platform as well, which has currently got the name Tissue Forge as an Anvil. That's particularly fancy. It can run 250,000 cells in real time. So that's pretty impressive. So and that exploits parallelism, all sorts of things. That should be coming out this year, I think. So what else? One thing, can one of you, Lucian or somebody, or Janice, can you go to this website, sys-bio.org? So sys-bio.org, and then it says then when you get to that page, it says go to the official site, click on that.
Yeah.
What do you see?
It says it's redirecting, and then it asks me to log in with Google.
Ah, there's a rights issue then. What about you, Janice? What happened with you?
Yeah, I have to also log in. I can share my screen right now.
Yeah, I have a quick show. Oh, there's some rights issue.
So
You just logged in, did you?
I had to log in, yes.
Yeah.
All right. I'll investigate that this afternoon then. Why that is the case. Okay. Yeah. Okay. The other people are getting Other people are getting a 404. So
let's see here.
Don't know what happened there. Okay.
Here's your. Okay, the particular link for the 2022 workshop is. As I click the wrong Windows, there we go. That's going to be more advanced and is about more probably larger modeling. Was it like it's tissue modeling, right?
Yeah, tissue modeling.
So,
we don't actually have a name for the new one yet. We just settled on the technology just last week. We had some prototypes. We wanted to make sure that it could be used as a library for people to host in other applications. We don't actually have a name for it yet, so we've got to come up with a name. If anybody's got some nice cute names they want us to. We could have a competition maybe. Come up with
SBW
an-
2.0.
No. This is just it's going to be a graphical network design application. So if you want to,
Does-
come up with some names, we can consider
Does
it.
Tinkercell still work if you find
Yeah,
it?
it still works.
So yeah, Tinkercell
Still
is
works.
another option.
Tinkercell still works. I don't know how
That's
SPML
not getting
compliant it is.
updated, but
No,
if,
not at all.
if it does what you want it to do, then it will continue to do that. But
But I don't know what kind of SPML export it does. It doesn't
Yeah.
support the SPML layout or render.
it should. Oops, sorry.
So SPML supports, there's another extension for SPML which allows you to embed network diagrams in the SPML. And we are starting to support that standard, and the new layout, the new visual engine will support that layout. So you'll be able to exchange, and Copasi, for example, can read that extension, SPML extension. So you'll be able to save your SPML models with that layout and render information as well. So
Was there a particular tool in SBW that was the layout?
it was Pathway Designer.
Pathway Designer, okay.
Yeah.
But it's only Windows?
Yep.
Okay.
Only Windows. Yeah.
Did you mention Cell Designer as well?
There is Cell Designer, but its export is incompatible with everybody else. So
The layout is, but not
The
the,
layout is,
SVML itself.
Not the
So
SVML, no.
So the SVML itself will transfer. You just won't be able to see your networks.
yeah,
see
it
them
doesn't.
quite the same way.
Yeah, it doesn't export standard layout information, which is a problem. Yeah.
But like someone was thinking of like designing a basic thing and a graphical thing and then importing it into Antimony and going on from there, that would work fine.
Oh yeah.
If you don't care about the
Yeah, we haven't showed
specific placement of your bubbles.
that. Yeah. All right. Any other questions? Otherwise, we can call it a day. We'll see you guys and gals tomorrow morning.